Welcome to this explainer on Quaternion rotations. In this video, I hope to give a comprehensive walkthrough of how to rotate objects in 3D space using maths, building up from absolute beginner level. At times, you might feel like, where is this going, or why is this relevant? But I promise it will all tie together by the end. A basic understanding of mathematics is assumed. Let's go. This device is called a gimbal. It has many uses, the most common of which is to keep cameras level for steady footage. This model is just an ornament and has no specific function. When you lay one flat, it looks like this. Now the point of a gimbal is that each of the 3 or more rings provides the ability to rotate the center object around a different axis. The theory is that 3 rings are enough to allow the gimbal to rotate in any direction. It's a brilliant idea and works very well for the things it's used for. But it does have one pitfall, which is a phenomenon called gimbal lock. This occurs when 2 or more of the rings are aligned, like so, and the effect of this is that 1 degree of freedom is lost. This means that there is at least one direction in which the gimbal cannot turn. This is a rather fundamental flaw for a device designed to point in any direction, don't you think? Well, not so much, because it can get there, it just can't go straight there. If we use a mathematical system of rotations based on a gimbal, called Euler Angles, it will have what's called interpolation issues. What this means is it would be very difficult to spin smoothly from one direction to another without getting weird flips and twists. So, we need a new way of doing rotations. Now, I'm going to go right back to basics and define what a rotation actually is. Well, in 2D, a rotation requires a point and an angle. The rotation is unambiguously defined by these 2 data points. The simplest rotations are around the origin, the middle of the graph. Here you can see an arrow rotating by a specific angle around the origin. If I replace that arrow with a point, then I can apply the same rotation to that point and it will end up in the same place as the arrow. So the rotation is entirely unambiguous. Now I'm going to move into 3D. What is a rotation now? Well, it still has an angle, but now, instead of a point, it has an axis. There is an entire line of points that do not move when the rotation is applied, and that line is called the axis. Here, the green lines each represent the axis of rotation. You can see that when the axis changes, so does the overall transformation of the cube. Now I'm going to digress rather massively. Anyone who has not taken maths past GCSE level and has come across square roots, so this includes all GCSE students, may have wondered why it is that you cannot take the square root of a negative number. I was confused by this as well. There's actually a very good reason why this doesn't make sense, and that's because it's not true. My maths teacher has described it as lying to children. It's taught that way just to simplify things. My personal belief is that this is a mistake. It does simplify things, but then they don't make sense. So here we go, right back to the foundation of maths, counting. I hope most of you are familiar with this particular mathematical object, but for those who aren't, it's called a number line. As you can see, each point on the line corresponds to a number. But then comes one of the interesting things about maths. You can always push the boundaries. So who said explicitly that the point had to stay on the line? Why can't it go up there? Well, let's see. I'll redraw my number line, and here I'm going to take the square root of 9. You hopefully aren't surprised by the result, but there's also a different answer. -3. You may say, how is this possible? How can a maths question have more than one answer? Actually, it's not all that rare, but in this case it is very interesting, because I propose a new method of finding the square root of a number that actually finds both at the same time, and the method I have in mind is not at all obvious if you have never seen it before. I'm going to draw a line to the point 9 and swing it round the origin. Every time it reaches the point 9, I'm going to write down the angle it has turned by. And now I'm going to halve that angle. And as you can see, each half angle is either a multiple of 360, i.e. 0, or 180 more. Which makes sense, and the two angles you get are the angles to the square roots. Trust me, this is not a coincidence. I'm going to go through that again, but this time using a negative number, just to see what happens. So, what is the square root of -9? I'm going to create my bar on the positive side, then swing it round, noting down the angle each time it passes -9. Now I'm going to halve each of those angles, and like before, they fall into two categories when you subtract multiples of 360. Now I'll create a new bar, the length of which is 3, the positive square root of +9, which was the length of the first bar. Now if I swing this bar around to the angles 90 and 270, here come my two very interesting points, which are clearly not natural numbers. In fact, because somebody has done this before, they have a name. Imaginary numbers, and you can draw them on a grid like a graph. Of course, then normal numbers also need a name, so they're called reals, opposite of imaginary, and the two names are shortened to IM and RE. And this plot is called the complex plane meaning a flat surface rather than an aeroplane, and these points are given values of 3i and -3i, I for imaginary. So now we can answer that previous question. The square root of -1 is called I, and it's not equal to any real number. And this number I is actually very, very useful. But first, I'm going to talk to you about complex numbers. Complex numbers are numbers that are built from both the real and imaginary units in combination. They work almost like coordinates or vectors, but they're actually way cooler. Addition and subtraction work the same way, piecewise. To add these two, I just add together the real parts, 2.5, and the imaginary parts, -3i. Easy. To subtract them, I can place them end to end like this, or subtract piecewise. 0 minus 3i. Right, on to multiplication. Here I have two complex numbers, and here I'll jump straight to their product. Now, you may notice that the angle to the product is the sum of the angles to the two operands. Also, the length, or magnitude of the product, is the product of the magnitudes of the two operands. Using some basic Pythagoras, we can determine this to be true. Pause the video and work it out if you haven't already. So now we can do something useful. I'm going to draw these as vectors, but just know they are complex numbers. If I take the numbers a and m and multiply them together, their product is p. Which is this point up here. What happens to p when I move a and m around? What's happening is that as long as m has a magnitude of 1, the multiplication by m corresponds to a rotation around the origin of the angle to m, which is exactly what we need. Let's dive deeper. This is called a unit circle because every point on the circle has a magnitude of 1. If I take my point that was m, I'll call the angle to that point theta. This point can be defined in another way, using the functions sine and cosine. Even if you've never used these functions before, you will likely have seen them just as buttons on your calculator. And now we can write this. This is a very special formula, and if you're interested, I suggest you investigate it more, but be warned that a fuller explanation does involve some pretty intense calculus. This is called Euler's formula after Leonhard Euler, who was a mathematician who lived in the 1700s. It basically says that by the magic of maths, this point can also be described by e to the I theta, which doesn't even make sense if you think about it, and that's because it's not real. It's imaginary. It can be proved true with rigorous maths, but it's by no means common sense. Now I'm going to take Euler's formula and replace both of the i's with u's. You'll see why in a minute. This is a sphere rotating in 3D space. That much you can probably see. Notice though that there are 3 different values controlling the rotation. Think back to the gimbal. This method of rotation is called Euler Angles, and the point I want you to focus on is that it required 3 different angles. These angles are commonly known as yaw, pitch, and roll, and also as
odchylenie, pochylenie I przechylenie.
but only in Polish. So how can we do 3 angles in one with only one magic unit, I? The answer is actually very simple when you think about it, although not obvious. So what we currently have is a complex number, but we need 2 more units, 3 different imaginary units. That will let us do 3 rotations in one. This type of number is called a quaternion. It requires a little more trust the process than complex numbers because it cannot be visualized so easily because it's 4-dimensional. Best not to even try. Quaternions are often written as the sum of a real number and a vector part. And also, they're often written in brackets. Now, if I show you again my modified version of Euler's formula, you can see what u means. U is my vector part. It can really be any letter, but I like u. And I'm going to hide this entire expression in a little box labelled q. Q is now what's known as my rotation quaternion. But back to complex numbers for a second. I'll define the 4 corners of a complex square multiplied by q, which is temporarily a complex number again, expressed by e to the I theta. And watch what happens when I change the angle theta. Each point traces out a perfect circle around the origin, which I can prove by leaving a trail behind each point. Let's move back up to 3D. Here is a cube around the origin, multiplied by q, my rotation quaternion, and u drawn in as a green line. Here, u is expressed in terms of its I, j, and k components as a 3 vector. See what happens now when I increase the angle theta. Well, it's definitely spinning around the axis, and if you're wondering where that came from, then you've actually made a good observation because it's not self-evident. It's because, just like the axis of rotation in 2D, a vertical line sticking up out of the page was perpendicular to both the imaginary and real axes, u is perpendicular to both itself and the real axis through some 4th dimension. For slightly more advanced listeners, this can be proved using vector cross products. But that's not important right now. What is important is that the cube is also spinning through that 4th dimension, but since you can only see one part of that spinning, it looks like the cube is collapsing and expanding, which is very weird. And now, as many of you probably know, when you hit a problem like this in maths, you just have to try random stuff until you find something useful. So, my first idea is to leave a trail behind each point to see what shape they trace out, as I did in 2 dimensions. pretty, but not looking very insightful yet. My next idea is multiplying by q on the left of the point instead of on the right. Interestingly, this is not the same thing because quaternions are non-commutative, which means pq is not equal to qp. You may be thinking that I've gone mad because it's doing exactly the same thing as it was before, but just wait a second, because after this I'm going to show you both cubes at the same time. See, this is not the same result. The cube multiplied from the left actually rotates in the opposite direction as the cube multiplied from the right. So what now? That revealed nothing, as insightful as it was. My idea 3 is multiplying by q from both sides. It's a subtle difference from what you just saw because it's only one cube, not two. Let's see what happens now. Well, it's certainly interesting and we're getting somewhere, but that's exactly the opposite of our goal. The rotation has cancelled out and the stretching has added up. There's only one fix for this, and it should be the final solution. If I make the second cue have a negative angle, then the rotation should add up and the stretching should cancel out instead. The terminology for this is the conjugate of q, and it's denoted with either a dash or a star, like this. And suddenly the cube is rotating. No more squashing effects at all. If you didn't quite follow the process that I took to reach this stage, then I suggest you go back and watch it again. And I'm just going to try moving the axis around a bit to see if it still works. Yes, it appears to be working perfectly, and another thing you might notice is that the interpolation between different axes is completely smooth. There is no gimbal lock. This is one of the greatest features of Quaternion rotations. Now, the next step to implementing this is to understand quaternions a bit better. Wikipedia has a lot to say on the matter, including images like these, which honestly I don't find very helpful at all. This one is helpful, but is not interesting. You can see it's a table of how to multiply the quaternion units together. This is the entire page on quaternions. It's a fountain of knowledge, but it's all buried in dense maths that I wouldn't wish upon anyone. So what I'm going to play next is what I wish had been on that page. I mean, look, it just goes on and on. I couldn't read all that. Okay, so here's a plot of the three imaginary units. And this is the first identity. Watch this because it explains the rules of multiplication in a geometric way. All of these identities are true, and the best thing is that I can do this with any combination of positive and negative axes. In fact, I'm going to write down all these rules in a chart. We already have I squared is minus 1 from complex numbers, but now we can add our new units into this formula. And also, all 6 permutations of the 3 units in pairs. You can see the nice cyclic structure that links to the geometric approach. Try to remember these identities. Pause the video here if you need to. Let's get into the meat of quaternion cross products. If you want to use this in coding, and honestly I don't know where else you would want to use it, you need to be able to actually carry out the multiplication, and most programming languages do not have a quaternion multiplication function. So we need to do it the old-fashioned way, which is multiplying out brackets. Observe and try to follow along because it's very intuitive. So I've multiplied out the brackets. The next step is moving the units to the end, being careful not to change their order. The wide values I can rearrange safely because they are just real numbers. Now, wherever there is a pair of units together, you can apply the unit multiplication identities. And now simply move the minus signs to the start of the terms and remove the brackets. Now, each column is going to get reordered, so all the units line up on each row. And I'll bring them together. But we can also factor out units, like so, leaving a neat equation. And if you look at this for a minute, you'll start to see patterns which will make it easier to remember. Not that you have to remember this, it's a very massive equation, but if you want to try it, then go ahead, because it always saves time knowing equations. Well, now you have the power to multiply quaternions to your heart's content, and you can freely rotate objects in 3D space. And if I didn't mention it already, Quaternion Rotations are free of gimbal lock. They have absolutely no downside, and they're used by pretty much every 3D software. Now, go and make something amazing.